Hello everyone and welcome to Sorting Algorithms, and today I'll be talking about heap sort. As part of my third year project, and in heap sort the first thing that again I'll be doing will be talk about the data structure. And now for the data structure, it is heap sort uses a binary heap, but it can be implemented using array-based data structure to implement that binary heap. The worst case time complexity for heap sort, it is O, big O, n log n, and then for the average case it is theta, n log n as well, and then for the best case it is omega, which is also n log n, so very consistent across the board. And then for the worst case space complexity, it is big O 1 because of the array and binary heap data structure. So what heap sort is basically is also a comparison based algorithm that's based on the binary heap, which is a complete binary tree data structure, which I will talk about in a few minutes. So basically, what I should talk about that now. So basically, what the complete binary tree or binary heap is basically where every level of the tree, so every element in a tree. So let's just say this is a complete binary tree where every node has at most 2 children. What binary heap basically is where every level, so this is one level, this is another level, so 1, 2, 3, there's 3 levels. So in every level, it contains a value stored in each node, and then the value stored in this node here, so let's say 6, the value below it must be smaller than 6, so 5 and 4, any order. And then in this one it works relatively the same, so 7, and then this can just be a 3. And then this one needs to be bigger than this one, which is in turn bigger than this one, which in turn is bigger than this one. So what you're essentially doing with a binary heap is finding the largest, with a maximum heap is basically finding the maximum element within that list. So let's just say 10. So so basically you know that 10 will be the largest, and this would be called a maximum heap. In turn you can have a minimum heap, which works exactly the same, so complete opposite actually. So let's just say here's 10 and 11, and then this must be smaller than both of these two, so I would say 9, and then 8, 6, and then if both of, 12, and then since this one is smaller than both these two numbers, and then this one is smaller than these two numbers, and then this one should be smaller than these two numbers, and these are in turn smaller than these, means that this one should be the smallest number in the list, so probably like 5. So this is basically what binary heap is. Contains values that are stored in a defined and definitive order, such that the value in the parent node must be greater or smaller than those in the children nodes. So what I'll be doing now is just to show you binary heap with an example. So the input array will be 4, 9, 3, 5 and 1, and that's with the corresponding indexes in the array. So what the algorithm does is first it has a build heap function, and that build heap function just basically first produce from the array of numbers will produce a complete binary tree, and then from that binary tree it will then produce what do you call it? It will produce a binary heap that's a maximum heap in this case, because you want to sort by ascending order. So basically they'll first take a root element, which is the first element, so it's 4 with index 0, and then it'll expand with 9, that's coming next, 9, 3, 9 with index 1, 9 with index 1, and then 3 with index 2, and then there's 2 children on 9, which is 3 and which is 5 and 1, and that's us. Yep. So this is what you call a complete binary tree. And that is defined as where every level within, this is level 1, 2 and 3, and that's where every level is filled except the last level, so filled with children, with 2 children on each node. So this is the complete binary tree, and now what we have to do is just build a maximum heap from this binary tree. So what happens first is we apply the heapify function onto the root node. So it'll compare 4 with 9. So in this case 4 will be so we know that 4 is bigger than 9 is bigger than 4. So that means there's a swap between these 2 nodes. So that'll be 9 and that'll be 4, and the indices will also swap 0, 1. And then after the root heapify is applied to the root node, it will apply to the nodes beneath that. So it will compare only node 4 because 3 has no children. Node 3 has no children, so it will apply heapify on index 0. And we know that 5 is bigger than 4, which is bigger than 1, so we swap 4 and 5. And so sort of things too, yeah. So what you have here is a maximum binary heap where the root element is the largest element in the tree, and all the elements beneath it have followed the same pattern. So 9 is bigger than all the numbers below here, and then 5 is bigger than all the numbers of its children. So 9 is the biggest element compared to all of its children. Since we know 9 is the biggest element, we will remove 9 from this binary heap and move it to, so the output will be the same size as your input, but we don't know what's the elements here yet because we don't know the order of these elements. But we know that 9, as the one we mentioned before, is the biggest element, so that's going to be placed last in the last index of the array. So this is essentially the sorted region, and then this is the unsorted region. And as we keep on recursively applying the heapify function, we'll slowly reduce the unsorted region by 1 and increase the sorted region by 1. So in a way we are decreasing the unsorted region until it reaches 1 element, and that will be the sorted element, and then we just move that to the first index of the array, and then the list is sorted. So what happens next is, since we know 9 is the biggest element, we remove it from the binary heap. So we remove it, and then we replace it with one of the current nodes. So in this case, it'll be one of the 2 children nodes, and it'll be node 1 with index 4. And then the same thing is recursively applied to the first node, the root node. So 1 is compared to 5 and 3, and we know that 5 is greater than 3, which is greater than 1. So 1 and 5 switch. The root node and the biggest node, the biggest element shall switch. So we swap 1 and 5. And same with the indices. Next, the keys. These are basically essentially the keys so the algorithm knows which indices to keep track of the indices in the array to control the switching. And then we apply heapify onto index 4, which is so the algorithm will apply it to index 4, which contains element 1, and then since it only has 1 children, it will only compare with 1 and 4. So 4 is bigger than 1, and in that case it will swap with 4 and 1. 4, 1, 0, and 4. So we end up in a scenario with another binary heap, maximum binary heap. So what we do now is remove the root element because it's bigger than all its children, and then place it in the next space in your output. So that'll be 5, and then we fill that with one of the smallest elements, and in that case it'll be 1, and that's index 4. So now same thing again, recursively apply it to index 4, the heapify function, and that will compare with 4 is bigger than 3 is bigger than 1, so 1 and 4 will switch, and so 4, 1, and that contains index 4, 0. And then so we know that 4 is now we arrive in a situation where it's a maximum binary heap again, and now we remove the biggest element, and place it in the output. And then it will be the same case as 1 will just become the root node, gets replaced. The root node gets replaced, succeeded by just one of the children nodes. And then what you have here is, again, the heapify function will be applied on index 4. So since we know that 3 is bigger than 1, so 3 and 1 will switch. 3 and 1 will switch, including 2 and 4. So now we know that 3 is the biggest element because it's a maximum heap where all the conditions are satisfied. And then we will remove the element 3 and place it in our next index in the array. So you can see the unsorted region is now much larger. The sorted region is much larger than the unsorted region with only 1 element left. And if since we removed element 3, we only have 1 node remaining with 1 element, which is 1, and that's considered the smallest element, and we don't need to reapply the function because this is kind of like the base case. So now we know since 1 is the smallest element, we just place it. We just place it here because it's the smallest element, and the list is sorted. And in the case of descending order, we produce something called a minimum heap, where all the comparisons are switched. So instead of the biggest element, we instead find the smallest element. And now I'll now be talking about the code of heap sort. So this is just a C++ code that I found on this website. This is heap sort. So this is where the algorithm starts. It starts with the build heap. So this is what so the algorithm is essentially trying to build a maximum heap. So first we'll try to build that complete binary tree, and then it will start shuffling, moving the largest element to the root node. So you can see that's where it calls the heapify function, and then from the heapify function you can see that it sets the largest node as the root node, and then it calculates the left and right children using these two formulas. So it's 2i plus 1, 2i minus 2. So that's the left and the right indices. That's the conversion process of converting a tree structure to an array-based structure, so it can be implemented much easier with less load on the memory. So this is where the comparisons take place, so comparing the child node and checking if it is larger than the root node, and if it is, then switch. So you can see this is where the assignments take place. And then this is the same for the right node, so this is the left node and then this is the right node. And then if the largest is not the root, it will swap. So once detected that the root node is not the largest, it will swap with the current element and the largest element. So if the largest element has been found and that's the current element, it will switch between the two. And then it will recursively call the heapify until it will recursively call the heapify function on the children node. So this is actually calling it on the children node and not the root node, whereas initially it's been called on the root node. But this is recursively calling, the number of recursive calls will depend on the size of the depth of your complete binary tree. So it will recursively call until it reaches a leaf node with no children, and that's in that case we'll see that the largest node will become the root node, and that's where the maximum binary heap has been successfully built. So then after that, what this for loop will do is this process is essentially what happens after you remove the largest element and then starting to replace the root node with and succeed it by one of the children nodes, and then reapply the heapify function. So you can see here the heapify function. So this is where you move the root to the end of the array. That's what this statement tells you. And then in this statement is essentially applying the heapify function on the root on index 0. So that's essentially the root node. So you're reapplying, you're calling the heapify function on the reduced heap, which is essentially the heap after you remove the largest node. And as you can see, this for loop is executing until I is equal to 0, which means that's when your unsorted region reaches 0, and your sorted region is essentially has been adding more elements to it. So you can see that this will call the heapify function many more times, and the swap will also, and the move the current node to the end will occur many more times. So that's when the next largest elements are being found and then shifted to the array, the sorted regions of the array. So there you have it. So what I'll be talking about now is the advantages and disadvantages for heap sort. So as you know that the heap sort uses a array data structure. The worst case time complexity is the thing that we care about the most, is just O n log n. So that's the slowest algorithm will run, which is much better than the worst case of which is much better than the worst case of quicksort, which is O n squared. So that's definitely an advantage in favor of heap sort. And also heap sort is actually an in-place algorithm, and what this means is it doesn't require extra additional data structure at runtime to move elements of one array to another, so you don't need that extra memory to store an additional array. So that could slow down the algorithm in a way, and this is much better compared to like merge sort, where that requires extra additional data structure to create another array and then move elements between that array. If you haven't done so, you can check out my merge sort video where I talk more in depth about that. But essentially, this requires less space complexity, because the worst space complexity for this algorithm is just big O to just linear. It's linear compared to it's just O1 actually. It's not even linear. It's big O to 1, and compared to merge sort, which is O(n), which is linear, that could hinder your performance of your algorithm. And also, heap sort can be implemented using array-based structure, like I mentioned before, instead of implementing it using a tree-based structure, and that will reduce the space and memory consumption furthermore. And then the disadvantages of heap sort is it's not a stable algorithm, and what that means, not stable. Oops. So it's not a stable algorithm. And what this means is, what not stable means is operations on the heap can change the relative order of equivalent of equal keys. So if you consider elements, so basically a not stable algorithm, a stable algorithm will produce and will output something like this: 1, 2, 3, 3, and 4. So this is sorted, but because there's two duplicate elements, and let's just say the input array was something like 3, 2, 1, 3, 4, and this is the index. So you can see 1, 3 has index 0 and 1, 3 has index 3, and then a stable algorithm can differentiate between these two keys, can take into account of the order, and once it sorts the numbers, it will actually also take into account the order, so this will be the 3 with 0, and then this will be the 3 with index 3. A not stable algorithm will essentially produce the same the same output array, but instead they will not they will change the relative order of these keys. So this will have index 3 and this will have 0. The last disadvantage is not practical compared to algorithms like quicksort, even though I mentioned earlier that it has a better heap sort has a better worst case complexity. but if you run quicksort side by side with heap sort, you know that quicksort is actually much more practical and faster compared to heap sort, because quicksort does not reach the O(n)², the worst case time complexity. as much. So in a way, quicksort completes much faster in practice.